we have been talking about acid-base chemistry. We looked at the Arrhenius model and the Bronsted-Lowry model. And then we looked at the auto-ionization of water and the pH scale. What we're going to look at now is how to calculate the pH of solutions containing strong acids and bases. And after that, we can begin to look at weak acids. But strong acids are a little bit more straightforward. So we're going to start with those. So first of all, what is a strong acid? Right? Strong acid All right. So a strong acid is anything that dissolves in water and dissociates completely. That's what makes it strong. Complete dissociation in water to yield H+ ions. So we can do kind of a generic definition. Any species HX dissolves in water and dissociates completely, that would be a strong acid. And strong acids are easy to work with because 1 mole of strong acid is going to give you 1 mole of H+. So if you got 0.1 molar of some strong acid, that's going to give you 0.1 molar H+. If you've got 0.05 molar of this acid, you'll have 0.05 molar H+. And that makes all of the math easier. Okay. There are also weak acids. Those are some that dissociate to give H+ and X-, but there's an equilibrium, so they don't dissociate completely, and the math gets a little more complicated. Okay. We're not going to talk about those here, but that is another set of acids. All right, so this is the definition of a strong acid. And one of the things you have to do is to be able to tell the difference between a strong acid and a weak acid. And the easiest way to tell the difference is to memorize the list of strong acids, because it's a fairly short list. Memorize the species which are strong acids, and then any acid that's not on that list is therefore by definition going to be a weak acid. So you don't have to memorize all of the weak acids, just memorize the strong acids, and anything that's not on the list is weak. Okay? So the first group of strong acids are pretty easy. These are the binary acids. So acids composed, well, I do this in class all the time. I'm pointing over here because there's a periodic table over here on my right. Of course, you guys can't see it. But anything, these are the halogens here: hydrochloric acid, hydrobromic acid, hydroiodic acid. So binary acids formed from the halogens are strong acids, but it's important to remember hydrofluoric acid, which is also a halogen. Hydrofluoric acid is not a strong acid. Okay? It's actually one of the weak acids. So for the binary acids, it's these three. Okay? Then there are two common oxyacids whose names are probably familiar to you. Nitric acid is a strong acid, and sulfuric acid, H2SO4, is a strong acid. Okay, so those 5 are pretty simple and straightforward. And then there are 2 that are probably a little bit less familiar, and that's chloric acid, HClO3, and perchloric acid, HClO4. Okay. This list of 7 that list of 7 strong acids you should commit to memory. Then when you're working problems and you see any one of these, you say, I know that one, that's a strong acid. If you come across an acid that's not one of these, then you know it's a weak acid. All right, and that's how you can distinguish between the two. All right, let's do a simple calculation. All right, so the question is, what is the pH of a solution of 0.25 molar HNO3, or nitric acid? All right, so you get a problem like this, the first thing that should happen is you see nitric acid and you say, I know that one. That is a strong acid. Okay? And because this is a strong acid, know that it's going to dissociate completely. So every mole of nitric acid is going to give us 1 mole of H plus ions. All right. So if we have 0.025 molar nitric acid, that's going to split apart. Every nitric acid molecule is going to break apart into H plus and NO3. So the concentration of H plus is going to be 0.25 molar. All right, let me go ahead and write that here. Okay. So we know that just because nitric acid is a strong acid. All right. Now the question didn't ask about concentration of H plus; it asked about the pH. So we need to calculate the pH. The next thing that we should be thinking is, because nitric acid is an acid, right? We know that the pH has got to be less than 7, right? A neutral solution has a pH of 7. A basic or alkaline solution has a pH greater than 7, and an acidic solution has a pH below 7. And so, since this is an acid and a strong acid at that, the pH should be significantly below 7, maybe a pH of 1 or 2, somewhere in that ballpark. All right. Then we can go to our definitions. Okay. Remember that the pH is the negative log of the hydrogen ion concentration, which is 0.25 or 0.025 molar. So grab our calculator. So the log of 0.025 is negative 1.602. The pH definition has a negative in it, so those two negatives cancel out. And so the pH is 1.6. All right, lovely. Okay, you remember in our last video we had the wheel of acidity, where you could start with the hydrogen ion concentration, calculate the hydroxide concentration, the POH, the pH, and then back to the H plus, or you could go the other way around, calculate the pH, the POH, and the hydroxide concentration, and back to the hydrogen ion. Okay, so for this problem, you could calculate all of those other variables. And if I give you a problem like this on a test or a quiz, I would probably ask you to calculate all of those because they're all fun. And there's no reason you want to limit the fun. I mean, this is only 25% as much fun as you can have with this problem. Why not have 100% of the fun? So I would encourage you, as you're working through your notes, maybe pause the video and take this value, work yourself around that wheel of acidity, calculate all the other values, and then come back up to the H plus concentration and see if you get 0.025. All right, so strong acids are really just that simple. The only thing you have to do is be able to recognize a strong acid, and then when you get that problem, write your dissociation equation and calculate the pH as we just did. It's very simple. All right, so let's look at strong bases. So just like with strong acids, definition of strong base is any species that dissociates completely in water to yield OH hydroxide ions. Okay? Now one of the keys here is that in order to dissociate completely, it's got to be soluble. So I'm going to write this as a solid. So if you've got something like sodium hydroxide, this is soluble. When you put it in water, it's going to dissociate completely to give you sodium ions and hydroxide ions. And again, the stoichiometry is such that 1 mole of sodium hydroxide gives you 1 mole of hydroxide ions. Okay? But this is not the case for something like iron 3 hydroxide. Okay? If you remember back to the solubility rules from Chem 105, most of the transition metals, the hydroxides of the transition metals, are insoluble. There might be a couple of exceptions. I don't remember any offhand, frankly. Generally speaking, most hydroxides are insoluble, except for group 1 hydroxides and a couple of group 2 hydroxides. But in any case, iron 3 hydroxide, definitely not soluble. And so since it doesn't dissolve, it can't break apart in this manner. And so iron 3 hydroxide is not a strong base. Okay. All right. I want to put one other one up here. As I said just a minute ago, all of the group 1 hydroxides are strong acids: lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide. That's pretty rare. You're not likely to come across that. But the others you would. And most of the group 2 hydroxides are also soluble. Magnesium hydroxide is not. Beryllium hydroxide, you're not going to come across that, so you can ignore that one. But lower down on the table, calcium, strontium, and barium, those hydroxides are completely soluble. So when you put calcium hydroxide in water, it's going to break apart completely to give you calcium ions and hydroxide ions. Okay? And you should see a problem with that. What did I leave out of this equation here? Right. You need a 2 there. Okay? And that's the reason I put this one up here, because I wanted to point out when you've got the hydroxides of group 2, the soluble hydroxides, calcium hydroxide, barium hydroxide, strontium hydroxide, when they dissolve, they're going to give you 2 moles of hydroxide. So you need to take that 2 into account when you do math to determine the pH of the solution. All right, let's do an example. Okay, so what is the pH of a solution? I left out the word solution, but what's the pH of a solution of 0.15 molar lithium hydroxide? All right. So when we see this, we recognize that as a soluble hydroxide, which means it's a soluble ionic compound. It's going to break apart completely to give ions in solution. So, since it breaks apart completely, every mole of lithium hydroxide is going to give us 1 mole of lithium and 1 mole of hydroxide. So, a solution that's 0.15 molar lithium hydroxide is going to give us 0.15 molar hydroxide. All right? So, all right, so far so good. Okay. Now the question asks us for the pH, right? Last time we just took the negative log of this number. Okay. We can't do that in this case though, because when we're working with strong acids, we had the H plus concentration. Here we've got the hydroxide concentration. So we've either got to use the hydroxide concentration to get the H plus concentration and then the pH, or use this to get the POH and then the pH from that. In this case, let's go ahead and use this to get the H plus concentration and then the pH. Okay. All right, so we remember that Kw is the product of the hydrogen ion concentration times the hydroxide ion concentration. Therefore, hydrogen ion concentration is going to be Kw divided by the hydroxide concentration. So that's 10 to the minus 14 divided by 0.15. Okay. And this is going to be a very small number, which we would expect, right? Because since this is a lithium hydroxide is a base, the solution is going to be basic, so the concentration of H plus should be very small, right? I got 6.7 times 10 to the minus 14. Just a second, I want to double check that because I was typing in the calculator and running my mouth at the same time. I want to make sure I didn't screw that up. Okay, yeah, that's right. All right, so this is our hydrogen ion concentration. That's 14. All right. So now we can get the pH since we've got the hydrogen ion concentration. pH is negative log of the hydrogen ion concentration. What do we expect the value to be here? Is a pH of 3 reasonable? How about a pH of 13? How about a pH of 7? 8? 4? What do you think? Well, lithium hydroxide is basic. It's a strong base, and it's fairly concentrated. 0.1 is fairly concentrated. So the pH should be greater than 7, and it should be significantly above 7. So probably a pH of 12 to 13, somewhere in that ballpark. Okay. All right, let's carry on. So the log of 6.7 times 10 to the minus 14 is negative 13.18. And so the pH is 13.18. And that's our final answer for that problem. All right. Again, if you want to, you can use the pH to calculate the POH. And from the POH, calculate the hydroxide concentration. And see if you get the 0.15 that we started with. All right. I just want to do one more example here with strong bases. All right, so what is the pH of a solution of 3.6 times 10 to the minus 4 molar barium hydroxide? Okay, and so just like last time, you should recognize barium hydroxide is a soluble hydroxide compound. That means it's going to break apart completely into ions, and that means that it is a strong base. But because of the stoichiometry here, each mole of barium hydroxide is going to yield not 1, but 2 moles of hydroxide. So a solution that is 3.6 times 10 to the minus 4 molar barium hydroxide is going to give us twice that concentration of hydroxide ions, 7.2 times 10 to the minus 4 molar. Incidentally, concentration of barium is going to be what? Right? 1 mole of barium hydroxide gives us 1 mole of barium, so that one will just be 3.6 times 10 to the minus 4. You don't need that for our calculation. I just wanted to throw that up there. All right, so there's our first step. We've got our hydroxide concentration. We need to know the pH, and we could do what we did last time use this to calculate the H plus concentration. But let's go the other direction around the wheel of acidity this time. We'll use the hydroxide to get the POH concentration, or excuse me, the POH, not concentration. So POH is negative log of the hydroxide concentration. So that's negative log of 7.2 times 10 to the minus 4. And log of that is negative 3.14. So those negatives cancel out. All right. So our POH is 3.14. Okay. That might seem surprising because our solution is basic, so we'd expect this to be greater than 7, right? No, right? Not right. I said not right, right? Anyway, this should not be higher than 7 because this is the POH and not the pH. Our pH should be greater than 7. All right, so let's calculate that pH. Okay, remember our last equation in our wheel of acidity is pH plus POH is 14. So if we subtract the POH from both sides, we get 14 minus POH. Like 10.7 something, 10.8 something. So our pH is 10.86. All right, terrific. All right, so for strong acids and bases, the math is really pretty simple. The only tricky part, well, I wouldn't even say tricky parts, but the things you need to focus on are, one, you have to be able to recognize strong acids and strong bases. To recognize the strong acids, you've got to memorize that list, right? And that's the binary hydrogen halides, hydrochloric acid, hydrobromic acid, hydroiodic acid. Okay? Hydrofluoric is in that column, but that one is a weak acid. That one is not part of the list. It's just those three. Then plus the two very common strong acids, nitric acid and sulfuric acid that you're familiar with, and then two slightly less common, chloric acid and perchloric acid. That group of 7 is your list of 7 strong acids. Make sure you memorize those. Any acid you come across that's not on that list is going to be a weak acid. All right. For the bases, any hydroxide compound that is completely soluble in water is going to break apart to give you hydroxide ions. That is the group 1 hydroxides, lithium, sodium, potassium. The others as well, but they're much less common, rubidium and cesium. You probably wouldn't encounter those. I don't think I'd ever seen those compounds myself. And then in group 2, not beryllium and not magnesium, but the ones below that, calcium, strontium, and barium. Those hydroxides are also strong bases. With the group 2 hydroxides, you also have to remember that each mole of base gives you 2 hydroxides instead of just 1. So you got to remember that factor of 2 when you're doing the calculations. Okay. Other than that, it's pretty straightforward. You just get the H plus concentration or the hydroxide concentration, and then just work your way around the wheel of acidity to calculate whatever you need. All right? Great. have fun with those, and we'll be back with another video tomorrow. I guess we're getting close to the end of the course. We'll look at weak acids next.